lecture 44. So yesterday we were talking about the virtues of taking averages of FFTs of windowed data. Okay, so the FFT record is not to be record length is not to be confused with the total data record length, right? So the total data record is chopped up into many chunks. You take windowed FFTs on each one of those chunks and average the magnitude squares. Okay, and if you go into the signal processing textbooks, you will find that there's a whole lot of theory behind this. And as far as we are concerned, we just interested in using the tool and not understanding, not particularly get into the very detailed aspects of the tool. And unlike in signal processing where the signal is unknown and you're trying to estimate its frequency or something like that, for us everything is known. We are putting in our sine wave, we know its frequency. The only thing is to make an intelligent choice of the window and so on. So this Hanning window is very popular for oversample data converter work for several reasons that I'll come into. And before I go, yesterday we were kind of I think trying to look at the PSD of the output of the delta sigma sequence with a rectangular window, and we guessed that with the rectangular window, because the discontinuities of the noise of the quantization noise waveform at the beginning and the end of the record, that looks like an impulse. So an impulse will have a flat spectral density. So you must see some kind of you should definitely not see the notch, right? So this picture is the hand windowed PSD, all right, and the blue spectrum here is the rectangular windowed PSD, both acting on the same data record. Okay, so as we expect, you see that there is this flat portion, and what is the band you are interested in? Where is your signal band that you are interested in finding the quantization noise? It's the band you are interested in is basically some guy here. All right. Okay. So if you use a rectangular window, you will measure some complete garbage, because most of the in-band signal to noise ratio you will be measuring is simply that caused by leakage of the FFT. It is not a true indicator of the delta sigma performance. Is that clear? Okay. So fortunately, MATLAB is a very convenient tool to just window the data with whatever window you want, and the hand window is often preferred in simulation work for the following reason. So for a FFT record of length n, okay, will give rise to how many points within 0 and fs by 2? Pardon? N by 2. So there will be n by 2 points between, or the resolution of the FFT is basically fs by 2 divided by n by 2, which is fs by n, correct? So n by 2 points in 0, fs by 2, but the band we are interested in is basically the signal band is 0 fs by 2 times OSR, correct? So how many points are there as far as we are concerned? We are trying to compute signal to noise ratio. Okay, so the number of bins that we are actually interested in is the first n by 2 times OSR points are in the signal band. Okay, all right. So okay, now looking at we have a variety of choices for choosing the spectral window, right? One is as we have seen, one is the Hanning window. the other one we saw in one of your assignments was this Blackman-Harris. Okay, the advantage of the Blackman-Harris is that while the main lobe is wider, all right, it's about 9 bins wide. The side lobes are the side lobe attenuation is much larger than the Hanning window itself. Correct. So the question is why shouldn't you be using I mean, if you have a wider main lobe and smaller side lobes, then that seems like a smart thing to do, right? I mean, so any comments on why one might want to use a Han window over a Blackman-Harris window? Yes. So what?
All the bins within the
Pardon? So please note that this is the FFT record length. Okay. All right. So if you want, and let's say we don't do any averaging, so this also represents the data length, right? So the simulation time that it takes to run a circuit, I mean, finally this is all going to be, I mean, MATLAB is alright for the beginning, but eventually you're going to get into circuits and transistors and so on. So you're going to be running simulations on an entire delta sigma modulator circuit with a lot of transistors, and depending on so if you wait for n clock cycles of the if you simulate the circuit for n clock cycles, then there will be n by 2 OSR points in the signal bandwidth, right? So if you want to simulate for the least amount of time, correct, what should you do? I mean, of course you want to, I mean, if you could go on decreasing n, correct, but what happens if you go on reducing n? The number of bins you have in the signal band will go on reducing, correct? So finally, if the n becomes so small, then you will have one signal bin and one noise bin, and that one bin, the first bin will be DC. Okay, so you will basically not be able to measure anything properly. So ideally, you would like to have the signal bandwidth to have a large number of bins. That's the bottom line, correct? But practical considerations during simulation dictate that you want, I mean, as small number of bins as possible in the signal band, okay, without losing accuracy, of course, okay, because you want to simulate for a short amount of time, correct? So, okay, so now given that you have so many number of points in the signal bandwidth, does it make sense to choose a window which has got a wide main lobe or a narrow main lobe? It makes sense to choose a window with a narrow main lobe, simply because if the signal spreads over fewer bins, then you'll be able to estimate noise better because you have larger number of bins for the noise. Does this make sense? This is just purely a practical reason during simulation. All right, and a rule of, I mean, what do you call, a thumb rule, if you may, is that the SNR is accurate if is all right if the number of signal bins is 20% of n by 2 OSR. And this is just a rule of thumb, okay? I mean, clearly if you'll be doing better if there are. So you need to simulate, if you have a given record length, you need to simulate for at least, I mean, okay, what is the minimum length required for an OSR of say 64? 128 times 5. You understand? So that you will have a reasonable number of I mean, so you can do a SNR with some degree of competence. So you're not relying on 1 bin or half a bin to compute signal and noise power. You understand? So for simulation, it always makes sense to use a Han window, simply because the Han window is nice and if the input tone lies on a bin, then the hand window will cause the signal to spread only to 3 bins overall, so 1 bin on each side of the tone. Does that make sense? Okay. For measurements, so for simulations, use a hand window. For measurements, what happens is, in many cases it is not possible to sync the clock source and the input signal source. Okay, I mean this hand window spreading to only 2 bins nicely is only when the input lies nicely on a frequency bin. Okay, if that is not true, then it will it will spread a little, it will leak to bins even on the side, and that becomes a problem. Okay, so for measurements, especially when you cannot sync the input signal source and the clock source, then it makes sense to use a window where the main lobe is wider, but it makes sense to use a window where the side lobe leakages is much smaller, which automatically means that the main lobe width becomes wide. Okay, and this basically, and if you want what do you call, if you want the signal power to occupy 20% of the number of bins, okay, then what happens if for the Blackman-Harris, what do we find? The signal kind of occupies about 9 bins or so, 4 bins on each side. Alright, so 9 bins, and so you want to have at least 50 bins in the signal band, right? So 50 bins in the signal band basically means that for an oversampling ratio of 64, you will need 50 into 128 or something like that, some 6,000 odd points. Okay, whereas for if you use the hand window, you will be able to do it with just 1/3 the number of points, because the hand window main width is 3 bins, whereas the Blackman-Harris is about 9 bins. You understand? In measurements, I mean, capturing a large amount of data is no big deal at all. It just boils down to amount of memory you can there is in the box that captures the stuff, and given that you can buy memory sticks with 4 GB at 800 rupees, it basically means that storage is no issue anymore. All right, so you can just simply grab huge amounts of data. So you can grab a lot of cycles, which basically means that this spectral spreading of the signal bin into many bins on the side is not an issue anymore. So for measurements, it makes sense to use a Blackman-Harris window, particularly if you are not able to sync the input signal sine wave with the clock. So even if the input doesn't lie on a F50 bin, you're okay. Does it make sense? All right. So that's the spiel on pass spectral density and how you calculate in-band signal to noise ratio. So the next topic is to actually sit and figure out how you implement figure out 3 things. So you have to figure out how to implement the loop filter and the quantizer, which is basically the ADC and the DAC. Okay, a quantizer is something which has got an analog input and an analog output. Correct. So what the modulator now becomes is, to take the more general block diagram, this is the quantizer. The quantizer needs to have is nothing but an A to D and a D to A. And where is your digital output? the output of this is your this is the sigma delta out. This output sequence is what must go to the decimator, which takes this digital sequence and goes and filters it off cleanly, so that the output is a very, very accurate representation of the input. So we have to figure out how to implement this chap, how to implement this guy, and how to implement this guy. We have seen how to implement A to D converters in fair amount of detail. So what kind of architecture do you think makes a lot of sense for the A to D here? Flash. Why? Yeah, okay, so what? If it's fastest, so what? So in general that whenever there is delay in a feedback loop, that's that's invitation to trouble, right? So in principle you want to use an A to D converter which does its job as quickly as possible, and the fastest architecture that we know of is the flash. And we know that a flash also becomes very, very painful to do if the resolution becomes high, because the complexity of implementation is exponentially proportional to the number of bits you get in the flash. But thankfully this the whole idea, I mean the what do you call, the USP of this delta sigma converter is that you can use a sloppy quantizer, right? So which basically means that the resolutions that you're probably shooting for are modest to begin with. Okay, so you will find that most people kind of use flash converters with resolutions 4 bits and below. All right, occasionally you find people who do 5-bit flashes, but mostly it has been single bit, 2-bit, 3-bit, and 4-bit converters. A 4-bit is the threshold of pain where the implementation becomes is just about manageable, right? 16 comparators is all right, but 32 is kind of getting a little messy. So the flash we have done earlier, so I mean there's hardly anything to do here. The DAC, again, there are many ways of implementing it. One of them is a current steering DAC. All right. So that also I'll just gloss over very quickly a little later on. Right. The key point is the loop filter, which we have not figured out up to this point. And one thing that so in the simplest case, for example, what we saw was an example of a loop filter was say this chap here, where I pushed the Z inverse delay that the quantizer gives you into the loop, and this is the quantizer modeled with an additive white noise source. All right. So this is the first order loop filter in a first order delta sigma loop, and this is only acting on discrete time signals. Correct. The assumption is that U has already been. What kind of signal is U? It is discrete time but continuous in amplitude, right? So the assumption is that the input signal has already been sampled. So it turns out that there are so all that you need to do is basically design Z inverse by 1 minus Z inverse is nothing but an what kind of, it's nothing but an accumulator. It's a discrete time accumulator, correct? And any suggestions on how I might be able to realize that? Have you seen this already? So the accumulators can be made with switch capacitor circuits, right? So the switch capacitor integrator is one system where which keeps accumulating the input, and so if you have higher order systems, higher order loop filters, all you will do is you'll have many. If you have an nth order loop filter, then you will have n accumulators in the loop filter, and then you have some weighted summation of the outputs of each of these accumulators to give you whatever loop filter it is that you want. So this whole broad area of delta sigma, this way of implementing the loop filter gives rise to what are called discrete time. Discrete time delta sigma modulators, alright, and people have been doing this for the last 10-15 years. Okay, so there's nothing. This has now become quite what you call mainstream technology, and was the first. Once people figured out how to build huge digital filters on a chip without too much power, then the next natural thing was to basically start doing delta sigma modulation, where you do the analog with all discrete time circuits, and the output, which is a digital sequence, gets filtered using the on-chip digital filter to give you. So all some of the first applications for high performance delta sigma modulators were digital audio. Okay, so audio recording, where you need to take the microphone signal and then digitize it to high precision, so that when you have an orchestra, for example, you have many mics, and the signals from all the instruments are, it's not that you put one microphone here and one microphone there and record, right? It is basically you take the sound of each instrument, record each instrument separately, and there is all this mixing and all this other stuff done in software, right? So some audio engineer sitting and weighting this by some amount, and special effects and all that stuff. Okay, so all that is done later. All right, so digital audio was a big initial application point for a lot of these delta sigma modulators, right? Because digital audio typically is 15 to 16 bit resolution. Professional audio is 24 bit resolution, right? So, and getting resolutions of the order of 15 or 16 bits with ordinary architectures is very difficult, because if you want to get 16 bit resolution, presumably the circuits, the components that you use in making that A to D converter somewhere must have matching to better than 16 bits. For example, let's say that you wanted to build a 16 bit flash converter. Apart from complexity being very, very high, the resistor string must be matched. If you want to get 16 bit DNL and INL, the resistors must be matched to around 16 bits. Otherwise, you will find that the INL errors will be so large that you have the precision of the converter is compromised. Correct? On the other hand, delta sigma modulation is something where you can take a quantizer which is as bad as just 4 bits, put it in a feedback loop, and magically within the signal band you get signal to quantization noise ratio of the order of 16 bits, 17 bits, whatever, depending on how well you noise share. Is that clear? So, all right. So then people start asking the question, well, if this has to be a sampled signal, correct? Before you do sampling, you must, what is the operation you must do before sampling? Anti-alias, correct? So the question people start asking is, hey, if I need to sample here, if I had a continuous time input, right, u of t, I must put an anti-alias filter, okay, and then sample. Okay. See, oversampling greatly reduces the kind of anti-alias filtering required, but you do still need an anti-alias filter, correct? Because where are the, if this is the input signal, right, and you're sampling at fs, right, so the band that will all alias back into the input when sampled is basically this band around multiples of fs, correct? So the alias filter, the anti-alias filter is something that needs to reject the alias, alright, to sufficiently large degree to prevent noise from that band getting aliased into the signal. So the question a lot of people start asking is, hey, how about this? And we've seen, in your DSP class, you have seen the following, right? Let's say this is a digital filter, right? So it's some impulse response h of n. So if I put in a discrete time impulse, I will get some response like this. Okay. Now, I won't be able to tell the difference between a discrete time system and a continuous time system if, for example, if I took a continuous time impulse, correct, made this an input to a filter H1 of t and sample the output, correct, provided so if H1 of t was of this form, alright. So if that was the signal here, and if I sample this exactly at 1 over t, then I will get the outputs of the sampler will be precisely the same samples that the digital filter is producing or discrete time filter is producing, correct? You understand? So I can always realize a discrete time impulse response by taking a continuous time filter or continuous time impulse response and, of course, properly chosen, of course, and sampling its output. You understand? So I can take a continuous time filter and make it look like a discrete time filter by sampling. Okay. So what kind of transformation is this? This is what is called impulse invariance. Where the name of the game is to find a continuous time filter whose impulse response matches that of a desired discrete time filter at the sampling instance. Does that make sense? And we will see how it's put to good use here. So in other words, let's say you had a H of S as a loop filter, correct? And this is the quantizer. Okay. So where should the sampling be done now? At the output of the filter. Alright. So this is a continuous time filter, so it operates on continuous time inputs and continuous time outputs. The DAC takes a discrete amplitude signal and generates a continuous time discrete amplitude signal, right? So this is continuous time. What about this guy here? This is the continuous time input itself. No need to sample because sampling is done inside the loop. Alright. And what is this? Clearly, this is a continuous time signal. Alright. And this is discrete. And what about this signal? It's discrete time and discrete amplitude. Alright. So this family of converters where the loop filter is realized using continuous time circuitry but made to look like as far as the loop is concerned, as far as this quantizer is concerned here, the quantizer can't figure out if there is a continuous time loop filter or a discrete time loop filter up front, right? Because the magically the HFS has been chosen cleverly. So that it is indistinguishable from, the digital L of Z that, the discrete time L of Z that we would have put there if we were realizing a discrete time delta sigma model. Does this make sense? Okay. So, this family of data converters are what are called continuous time delta sigma converters. Okay. So let's sit and figure out. So I'm going to bypass the whole, there's a good 2 decades of work on discrete time delta sigma converters. I'm just going to bypass all of it and jump to continuous time. Continuous time have been around for the last maybe 10 years or so, and a lot of people, didn't realize the advantages they bring. It's only recently that a lot of people, especially when power dissipation became very important, that people started figuring out the virtues of continuous time delta sigma converters, and today everybody and his brother keeps doing these things. So I think it's most appropriate that I discuss them rather than sit and spend time discussing discrete time stuff. Okay. In any case, there's not time for both. So, all right. And needless to say, continuous time is a little more complicated than discrete time, simply because you need to know even things like sampling and impulse invariance and stuff that we've all probably long forgotten. Okay, and we need to be able to figure out how to transform filters back and forth between the Z domain and the S domain, which is asking probably too much, right? So there's a lot of resistance to applying stuff that we already know to a different situation, and that's why continuous time delta sigma converters are generally considered to be a tough area where it's kind of difficult to understand. But as you will see, there's nothing big. There's no big deal. It's quite straightforward. Okay, so let's start off with the simple things first. We want to build a first order. The first thing to do is start with the simplest thing. And what is the simplest delta sigma modulator that you know? The first order, a loop filter whose NTF is 1 minus Z inverse. Correct? So, in other words, you're looking for a loop filter with a high gain at low frequency or infinite gain at DC, and whose gain keeps falling off. Correct? So, what do you think? What is your intuition telling you? Integrator, right? So, let's try putting an integrator, which is what we were doing in the discrete time case also. We had Z inverse by 1 minus Z inverse, which is nothing but a discrete time integrator. Hopefully, a continuous time integrator will work also. All right. So, the output of this integrator is sampled. Correct? So this is U of t. The output is sampled, passed through a quantizer, which is nothing but an A to D converter and a D to A converter. The A to D converter adds some error. All right. And what happens to the D to A converter? The D to A converter takes the discrete time output and converts it into a continuous time output. So, is it just enough if I told you that it is a 3-bit DAC without telling you anything else? Is it just enough if I told you that I have a 3-bit DAC in the feed? In the quantizer. Pardon? No. That's all internal to the DAC, right? So if I told you I have a 3-bit DAC, it basically means that it takes in a 3-bit digital word and puts out a waveform with ideal. We need to know every DAC has to be associated with a pulse shape, because it is converting from a discrete time signal to a continuous time signal. Please note that the input to the DAC is only defined at discrete times, correct? Only at the beginning of a clock cycle or whatever, right? whereas the output of the DAC is a continuous time waveform where it is defined for all time. Is that clear? So we saw that a DAC, the continuous time output of the DAC has to be associated with a pulse shape, correct? So there, and what all pulse shapes did we see? The first thing was just the simple continuous time impulse, which is like a terrible thing to do, okay? Alright. The next thing is, we saw that, one other natural pulse shape is the so-called NRZ pulse shape. The other pulse shape that we know is the return to zero, and you can come up with any number of pulse shapes, so it's not a big deal. So bottom line is that there is a pulse shape associated with the DAC. Does this make sense? Okay. So in other words, what you have is this is a discrete time impulse, then it is understood that this is converted into a continuous time impulse. And how do we model the pulse shape? We can model it by a filter whose impulse response is P of t. Alright. So in other words, the output of the A to D converter is a discrete amplitude signal, okay. So that is converted conceptually into a discrete time, into a, you can think of the DAC as doing the following: it's taking the discrete time input and producing an impulse train, a continuous time impulse train of Dirac delta functions, which are then passed through a filter whose impulse response is P of t, right? And that is being fed to the output, to the subtractor here, resulting in a continuous time waveform, and the integrator basically operates on the difference between u of t and p of t.
So input of p of t are the impulses.
Pardon?
The input of p of t will be impulse train.
Yes, it will be a continuous time impulse train, correct. Okay, but what we are in, the output sequence here, so you can think of the fictitious analog, the impulse train generator to be sitting here. So the output here is still a discrete time sequence. You understand? Okay. So if I want to realize the same noise transfer function, what should I do? I should compare this with Z inverse by 1 minus Z inverse. This is what you had in the discrete time case. Alright. So if I want to have the same NTF, correct? What do you think I should do? How do you think I will be able to?
1 by 1 plus P of S by S must map to 1.
Okay. So in other words, there are many ways of doing it. One way is to make sure that the loop gain of both the loops is the same. Alright. So if this NTF is the same as this NTF, then if I break the loop, say here, apply an impulse, okay, what comes back here must be the same as what would come back here, okay. Does it make sense? Where? Yeah, everything is sampled, so it doesn't hurt if I put a sample and hold, right? You understand? Okay. Conceptually, this is what has happened. Yes, that's a good point. Yeah, it's understood that all the signals are sampled and held, right? So, if that's what, if these two, if the NTS of both these loops are identical, then if I break the loop, right after the sampler there and apply a discrete time impulse, what comes back after the sampler must be the same in compared to, must be the same as what you would get in the discrete time case. Does that make sense? And if I'm only interested in the noise transfer function, I know that in any case, the signal transfer function at low frequencies, okay, must be Can you comment on the signal transfer function at low frequencies for the continuous time 1? Should be 1 because the gain of the integrator is at DC is or at low frequencies is very, very high, which means that the DC component here must be the same as the DC component here, or the low frequency component here and here must be the same, which hopefully means that the low frequency component there and here must be the same. So our first job is to not confuse ourselves with the input at all. So we set the input to 0 in both cases. All right. Let's figure out what we need to get for the discrete time case. So if I break open the loop, what will I get? It is if I put in an impulse. Okay, so this is the E of n. I put in a delta of n here, and what will I get? This has to be multiplied by -1. If I put in minus delta of n rather, then what should I get? Z inverse by 1 minus Z inverse, and this is the out. This is what you will get after you go around the loop. Does that make sense? Rakshit, is it clear? So what I am doing is I have broken the loop here. Is that clear? Correct? Then I will apply an impulse here and measure what comes back after the sampler. Correct? If these two loops are exactly identical, then if I apply an impulse here and measure what comes back after the sampler here, okay, it should be the same. That's the idea. Is that clear? Samir, you're clear? Positive. Okay. No, if you're not clear, please stop me. There's no, Okay. So then, so now you tell me what I will get at the output. So please note that there was a -1 here, the corresponding to. Okay, let me just plot. I'll apply delta of n and measure what output comes out, and I'll plot the negative of the output so that I avoid all negative terms. Okay. So what is the output of Z inverse by 1 minus Z inverse when if I put in an impulse into Z inverse by 1 minus Z inverse, what is the output? Abhishek. No, instead of E of n, I will say I want the same noise transfer function. In other words, I want the same impulse response from E of n to the output of the converter, which is equivalent to saying that, see, the noise transfer function is nothing but 1 by 1 plus L of z, right? So if L of z was the same for the discrete time as well as the continuous time system, then I should have the same NTF. Is that clear? Okay. To find L of z, I mean the L of z is basically Z inverse by 1 minus Z inverse. I apply delta of n. What do you think will happen to the output sequence? Pardon? First sample will be, okay, if I, for those of you who not realized it, what is 1 by 1, if I put delta of n to 1 by 1 minus Z inverse, what do you think you will get? It's the impulse response of an accumulator, right, and which is U of n, right? So 1, 1, 1, 1. Z inverse by 1 minus Z inverse will give you a 1 sample delay. So the output will be alright, so this is 0, this is 1, 2, 3, 4, 5, 6, 7. So
While designing the thing,
yes,
we had pushed one Z inverse from the
quantizer to
quantizer. So
correct.
While generating the loop filter transfer function, we should push back that Z inverse.
Yes, okay. So let me come to that. For the time being, we are assuming that the quantized is at 0 D. Yes, sir. Okay, so let me explain this again. So you can see all right. Okay, so you want the same. This discrete time modulator has got a noise transfer function, correct? And what is the noise transfer function by definition? It is 1 by 1 plus loop gain, correct? So, in other words, if I want to find the impulse response corresponding to the noise transfer function, what will I do?
Look at the output.
I will inject an impulse here, a discrete time impulse, and look at the discrete time output sequence that comes out of this thing, okay? And if the two loops, the continuous time loop and the discrete time loop are identical, then if I put a delta of n here, the discrete time sequence which comes out here must be the same as the discrete time sequence that comes out there. Does that make sense? Alright. So rather than deal with 1 by 1 plus loop gain, alright, you might as well deal with loop gain, okay, which means I can cut open the loop and then figure out what I should do to make the top one equivalent to the bottom. Is that clear? Okay, Samir, you're clear now, okay. So all that I have done is cut open the loop, the loop filter comes by, I push in an impulse, and lo and behold, the response at the output of the loop filter is an integrated delayed version of the impulse, which is the u of n minus 1. Yeah, there is a negative sign which I'm going to neglect on both sides, so I can avoid drawing negative numbers. Does it make sense? Yes, sir. Excuse me.
How we are getting this as your give delta n?
Yeah, what is delta n? What is delta n?
That is at 0 will get 0.
It is 1 at 0 and 0 throughout. Alright. 1 by 1 minus z inverse is nothing but 1 plus z inverse plus z to the minus 2 and so on.
How we are getting this?
Okay, the hack is this is a geometric progression, right? As long as mod z is less than 1, this is true. This is an accumulator.
Okay, binary extra.
Okay, so no, 1 by 1 minus z inverse is nothing but an accumulator. So it keeps accumulating the input. If the input is 1 and you go on accumulating it, then the output should be 1 all the time. Yes, and the z inverse is going to push that out by 1 sample. Is that clear? Very good. Now, if we did the same exercise for the continuous time loop filter, what should I get? Delta of n, and please note that this delta of n is implicitly the DAC getting converted into a delta of t and getting applied to a loop filter whose to a filter whose impulse response is p of t, correct? So equivalently you can think of it as delta of t being applied to a filter of impulse response p of t. This output is going to 1 by s, whose output you are sampling. Does that make sense? That's what the DAC is doing. The DAC is taking a discrete time sequence. Let me just clarify that because it's important. A DAC The job of a DAC is to take a discrete time, discrete amplitude input signal and convert it into a continuous time discrete amplitude signal, correct? So I can interpret going from here to here in the following circuitous route, okay, which is first thing I do is conceptually convert the discrete time impulses sequence into a sequence with continuous time impulses and then pass this through a filter whose impulse response in this particular example is 1. So this is P of t, correct, and that comes here. It's only conceptually, this is what is happening in a DAC, okay. You put in discrete stuff and you get a continuous time output waveform, but that can be understood to analyze spectrum and all that by in this manner. Is that clear? Very good, okay. So for all practical purposes, this is exactly the same thing that I have said here. So convert the discrete time impulse in the DAC. The discrete time impulse is converted into a continuous time impulse, right? And that gets applied to a filter whose pulse shape is P of t, correct? And that goes to the loop filter, which happens to be 1 over S in our case, and the output is sampled. Clean? Okay. Now, of course, so clearly the first thing that comes out right away is that the NTF or the loop gain depends on, definitely depends on 1 over S and P of t. So the pulse shape of the DAC influences the loop gain, which means that the pulse shape of the DAC influences the noise transfer function. That makes sense? So you understand? So let's take a couple of pulse shapes that we know. The first thing being the NRZ pulse shape, because that's the most natural pulse shape we can think of. So delta of t, this P of t is nothing but, okay, and for argument's sake I will normalize the sampling rate to 1 Hertz so that I don't have to keep writing TS everywhere, alright. So this goes from 0 to 1, okay. The sampling rate TS is 1 second, sampling time is 1 second, sampling rate is 1 Hertz, okay, and this goes to an analog integrator or a continuous time integrator 1 over S. So if I now put in a pulse like this to an integrator, what is the output I will get? Yes, Subrato. If this was the input to an ideal integrator, what will be the output?
Okay, it will go on ramping and then
it will go on ramping for how long?
For
1 second, correct?
And then it will be continuous, flat.
It will be flat, right? Okay. So what will be the value when it is flat? It will go on ramping up for 1 second, and what will be the 1? Okay. Now I am taking the output and I am sampling it. So at 1 Hertz, alright. So what is the discrete time sequence I get? So 0, 1, 1, 1, blah blah. Does it make sense? alright, and this basically means that the NTF of this chap and this guy are the same. Does it make sense? So what we have realized is in effect a continuous time first order delta sigma modulator. Alright. Okay, let's now try the same exercise for a return to zero pulse shape and see if anything changes. So what should be the what is the return to zero pulse shape? To have the same DC gain, I must make sure that the alright. So what is the output now? The continuous time output waveform definitely changes. Okay, so it goes up to it goes up to 1.5 the time, alright, and stays flat. So even though the continuous time waveform changes, the discrete time sampled response remains the same. So this also represents a noise transfer function with a delta sigma modulator with an NTF of 1 minus Z inverse. So as you can see, yeah.
There will be a delay in for data also.
Wait, 1 minute. Okay, so a critical question is what happens when there is delay in the quantizer. I will come to that. At this point, let's assume that we have ideal quantizers which give you their outputs, whatever, a fraction of a picosecond after they have sampled the input. Does it make sense? Alright. So one moral to take away from the story is that there can be any number of continuous time filters which all have the same what do you call the same discrete time equivalent once the outputs are sampled. For instance, you already seen an example like this. Another thing is in principle nothing prevents me from finding a continuous time filter which does this and then does this and then, okay. So if I put that continuous time filter in the loop, it would also give me the same NTF. You understand? So I will stop here. We will continue tomorrow.